Hello and welcome to this video on Lagrange points, where we're actually going to derive them from first principles, because I found many videos online that talk about Lagrange points and, what they are, what they're used for, what things can be found there and all that, but none of them actually derive them from first principles, which is a shame if you ask me, because they're actually not that difficult. As long as you've got an A-level understanding of maths and physics, you should be able to find them quite easily. So that's what we're going to do today. So first of all, what is a Lagrange point? Okay, it is a point where the centrifugal and gravitational forces in a planetary system cancel out, basically. It's really cool. So let's set up our planetary system. First of all, we've got a large mass, which we will call M1. Okay, and this is typically a star, but it could be anything. It could be anything of substantial mass. And then we've also got our orbiting body, which I will call M2. Okay, and a very important piece of information about this system is that M2 is much smaller than M1. Okay, so that just means, the size of M1 dwarfs the size of M2. I hope I've got that the right way round. Okay, and then finally, what do we want to do? We want to put some object, okay, which I will put out here, let's say, of mass little m. Yeah, you can just about see that. Okay, such that its orbital period is the same as the orbital period of M2. Now, orbital periods and the angular velocity due to gravitation are related by a factor of 2 pi. And that means all we have to do is find where the angular velocity is equal for both of them. Okay, so let's go ahead and put that in. Okay, we'll call the angular velocity omega. Okay, and they both move with velocity omega. Let's also put in our distances. So we'll call the distance between M1 and M2 big R, and the distance between M2 and little m, little r. Okay, so what do we need? Well, we need the forces due to gravity and centrifugal force, right? Okay, so let's go ahead and put that in. Okay, or put the equations in at least. So force due to gravity is G big M little m over d squared. Now, very important to note, the m's here are in no way related to the m's and M1, M2 and all this over here. Okay, these are just placeholders for the gravitational force equation. Okay, and we also have the force due to circular motion or centrifugal force, and that is given by little m omega squared d, where d is the distance to the body of orbit. Okay, and we actually have a formula for omega squared in a gravitational system. Okay, that is given by big G big M over d cubed, where big D here and this big D actually are the distances to the body of orbit, and big M is whatever that large body is. Okay. And one final thing that I forgot to mention is that this mass m, little m here, okay, is again much, much, much smaller than both M1 and M2. Okay, and that's it. Okay, we've set up our system, so let's go ahead and solve the system. Okay, so from the point of little m, okay, we have, or we want the sum of the forces due to gravity equal to the circular force, right? And I'm going to designate going left as positive, okay? This is just so that when we're working out the forces due to gravity, it's easier to work out and you don't have to worry about weird negatives coming and going and stuff like that. So what have we got? Okay, so let's first of all work out the force due to gravity from m1 on little m. Okay, so that is going to be g m1 little m divided by r plus little r all squared. Okay, then let's put in the force due to gravity of m2 on little m. Okay, that is going to be g m2 little m over little r squared. And this is equal to the circular force. Well, that's going to be little m omega squared. Well, we've got that, and we know that omega here is the same as the omega here. Okay, so we can use this formula for omega, and that will be g m1 over big R cubed, okay, multiplied by the distance from m to m2. No, m1, sorry. Yeah, the whole thing. So that is r plus r again. Okay. Now, one thing that we can do first straight out is we notice that all of these have a factor of big G and also little m. Now, big G is the universal gravitational constant, okay, so that's just a number, so we can divide through by it. It's never zero. And similarly, our mass m, even though it is much smaller, it's never zero because you can't have zero mass. You couldn't do that. So you can divide through by that as well. So let's go ahead and do that. Okay. So we end up with m1 over big R plus little r all squared plus m2 over little r squared, and that is equal to m1 over r cubed multiplied by r plus r, big R plus little r. Okay. Now, if you try and solve this for little r, what you actually end up with a quintic equation, and famously, quintics are very difficult to solve. Okay, so we've got to do something a bit clever. We've got to be a bit savvy here. Okay, and we use a binomial expansion on the 1 over big R plus little r all squared term. Okay, so let's go ahead and do that, and we will do that on a separate sheet of paper here. Okay, so I've got the binomial expansion formula here. Okay, and what it says is that if you've got 1 plus x all to the power of n, okay, then that can be expanded into this, all right? But if x is really, really small, okay, as in very close to zero, not exactly zero, okay, but very close, then this can be approximated to 1 plus nx. So let's do that with our r plus r all squared term. Okay, so what have we got? We've got 1 plus r plus little r all squared. First thing I'm going to do is I'm going to change this into a something plus something to the power of n term. So basically change that 2 into a minus 2. So we end up with r plus little r all to the power of minus 2. Okay. Then I'm going to factor out the big R, and we end up with big R to the minus 2 multiplied by 1 plus little r over big R all to the minus 2. Now, if we go back to our setup, okay, we can happily assume that little r is much smaller compared to big R. And that means that when you divide through here, this number is going to be very small. And it's that number that we can use for our x. Okay, so what do we end up with? We end up with r to the minus 2 multiplied by 1 plus minus 2 multiplied by little r over big R, and then all of that in brackets. Let's tidy that up a bit. Okay, and we end up with 1 over big R squared multiplied by 1 minus 2 little r over big R, all in brackets there. Okay, so now we've got this. Let's plug this back into our formula for the Lagrange point. Okay, so we have got big M 1 over R squared multiplied by 1 minus 2 little r over big R, okay, plus M2 over little r squared, and that is equal to big M1 over R squared plus M1 times R over R big R cubed. Okay, now all I've done here is I've just expanded this. Okay, so let's expand this set of brackets on this side. We've got M1 over big R squared minus 2M1 little r over big R cubed plus M2 over little r squared equals M1 over big R squared plus M1 little r over big R cubed. Okay, now we look at this and we go, well, I've got an M1 over big R squared here, and I've got the same term on this side, so they can cancel out. And similarly, I can collect the M1 little r over R cubed terms here and here. Okay, so let's do that. Okay, so what do we end up with? We end up with little m, big M2 over little r squared is equal to 3 M1 little r over R cubed. Now, we wanted to solve for little r, right? So let's bring everything, so little r is on one side and everything else is on the other side of the equals. Okay, so we can do that here. So we have little r cubed is equal to, make sure I've get this the right way round, M2 over 3M1 times big R cubed. Okay, now all we have to do, take the cube root. Okay, and we end up with little r is equal to the cube root of big M2 over 3M1 multiplied by big R. Okay, and so what this means is that, well, actually, that's it. That's the Lagrange point. That's where it is. And what it means is, first of all, the Lagrange point, it doesn't matter what mass of little m that you put in, okay? You know, that mass has no effect on where the Lagrange point is. The only things that affect it are the masses of the two bodies and the distances between them. And I think that's amazing. Now, I've been saying them when I refer to the Lagrange points, but as you can see here, we only worked out one. So there are actually 5 Lagrange points, and I'll quickly show them to you now. Okay, so if we have got our large body M1, okay, and M2 is orbiting on this sort of path. Okay, we assume it's circular. I mean, that's as close to circular as I'm going to get, right? Okay, so first point that we've worked out, and I'll do that in orange, I'll do them all in orange, is here, and this is actually the L2 point. Okay, there is another one on the inside of the orbit at L, and this is L1, and then there is a third point on the far side, which is L3, and these form a collinear line between them. Okay, and again, if you use a similar formula, okay, and get the positives and negatives of gravity in the right direction and all that, then you should be able to work out all three of these. Okay, and I leave that as an exercise to the viewer if you're interested. Okay, it's a fun exercise, I'd say. But the other 2 points are here and here. So the one over here is L4 and this one is L5, and we assume that it is an anticlockwise orbit, okay, or prograde as it's called in astronomy. Okay, and these points are situated such that if you draw a triangle between these points and M1 and M2, you end up with an equilateral triangle. These 2 points are 60 degrees away from the collinear line, which I think is pretty cool. And these three collinear points were actually originally discovered by Euler, but we call them Lagrange points because Lagrange was another mathematician and he discovered L4 and L5, okay, and so he's the one that's remembered. Fun fact about these points, L1, L2 and L3 are actually a little bit unstable, so if you put something there, you have to perform a lot of course corrections, to keep your objects there. But L4 and L5 are in fact stable, and they are so stable that you can end up with what are called Trojan asteroids. Okay, the first Trojan asteroids were discovered in Jupiter's Lagrange 4 and 5 points. Okay, and these are Trojans. These ones have capital T. Okay, and so if this is Jupiter and these are the Lagrange points and the Trojan asteroids, as they spin around, it's like if it was on a bicycle wheel. If you spin that bicycle wheel around, then the different points will never meet, and they'll just sort of move in unison. That's the whole point of having the same angular velocity. Okay, Mars also has Trojan asteroids, I believe, but these are Trojans with a lowercase t, and the reason is that Jupiter's were discovered first, and they were given a capital T, but then the Martian ones were discovered afterwards, and scientists were like, well, we can't name them the same thing because that would be confusing, so we'll just lose the capital, okay, and that'll make everything clear. Okay, but there we are. We've derived the Lagrange point, and you can check for yourself the formula actually works, because if you look up where the James Webb Space Telescope has been put, it's been put in this L2 point, and if you work out little r from this, you'll find that is precisely where the JWST is in space. And there you have it. That's Lagrange points. I hope you enjoyed it. If you did, hit like, hit subscribe, do all the stuff, and I'll catch you in the next one.